So welcome back. So in this network we are going to discuss the sequence network ZBus, how we are going to obtain the ZBus from a sequence network, means positive sequence network, negative sequence network and zero sequence networks, and symmetrical fault analysis also we have to consider in these lectures. So in previous lectures we already discussed the how we are going to get the sequence networks of a load, generators, transmission lines and transformers, and also draw the corresponding sequence circuits. So objective of this lecture is to construct the sequence networks using the positive, negative and zero sequence and obtain the ZBus forms and fault classification, and also we are going to analyze the symmetrical fault analysis. So here the construction of the sequence network of a power system, you know that we already discussed the three sequence components, that is the positive sequence, negative sequence and zero sequence. We observed that the positive sequence have the voltage source and impedances, while the negative sequence have only the impedances. There is no voltage source. Zero sequence have the only impedances and there is no voltage source. So in this way, we can summarize or we can write in terms of the network. So here we are going to represent or obtain the sequence network using a suitable example. So here I have taken the examples from the reference books. So here this network is connected the generator, having this generator is connected the star with grounded, having the terminal voltage 1.05 per unit. Positive sequence reactance is 0.15 per unit, negative sequence is 0.17, zero sequence 0.05 and xn is equal to 0. So this is this one is terms in the sorted, and this is the bus 1. Then there is a transformer connected the star primary side, sorry, delta is primary side, secondary side is star with grounded. And this is the transmission line, you know that the positive and negative sequence impedances are the same, that is given in per unit 0.105, and zero sequence they have given. This is the step down transformer reactance, and this is the step up. And there is a load, that is the balance star connected machines are connected here. So terminal voltage is given, positive sequence impedance and negative sequence, zero sequence and xm is given. So we have to just represent this network into the positive, negative and zero sequence due to a fault occurs at the near of this bus 2. So means near about the load locations. So this system becomes unbalanced, so we have to balance it, and before balancing it we have to draw the sequence networks. So we already discussed the sequence networks of the generator, then transmission, then transformers, then transmission line, then a loads. So we have to apply these conditions in these lectures. So here you can see this is the A equivalent circuit. So this is the, here we are considering this is the bus 1, this is the transformer, this one is the transmission line. We can write this is the step up down transformer, this is the bus 2, this is machine. So you know that the positive sequence have the voltage source. So we have to consider voltage source 1.05 angle 0, and this is the impedances. So generator impedances positive sequence is given, so we have to consider J 0.15, and transformers we have to, you know that the transformer positive and negative and transmission lines positive and negative both are the same. So there is they are not going to depend on the type of the connection of the transformer. So we can directly use it as a J 0.1 positive sequence is given. And for the transmission line, we have to also consider positive sequence. Here the step down transformer machine is also given the positive sequence J 0.2 having voltage source. So this is all about the positive sequence network. So here all the impedances we have to consider the positive. Remember that the transformer and transmission lines, positive and negative sequence we have to consider as a same. So here they have given positive and negative sequence for the transmission line and transformer J same, so they are considered. For the transformer they have given J 0.1 step down and step up transfer. Transmission line they have given 0.105, so we are considering. So here negative, when we are going to draw the negative sequence impedance, so just you have to sort out these voltages. So we have to sort out and replace these impedances with the negative impedances. These are the positive impedances we have to replace. So only the transformer and transmission line impedances are the same, positive and negative. So we are making as the same, only the load and generator we can convert the positive sequence impedances into the negative sequence impedance, which is already given, just you have to write. And for the zero sequence, so you know the zero sequence for the this is the A bus 1, this is the bus 2. So zero sequence is given, so generator is, there is Zn is equal to 0, only the Z0 will be there, so you have to connect from the bus 1, and here the Zn is the 3 times of Zn. So for the machine, so here the Z0 they have given, this is the Zy, so it's given, and 3 times of Zn you have to write. And transmission and zero sequence we can write in same way. But the transformer connections, transformer zero sequence depends on the types of connection. So you know that this is the Z0 of the transformer, first transformer. So primary side is connected the delta, secondary side is the star. So delta means P1 connection should be switch on and S2 will be closed. So S1 and P2 will be open. So that's why here there is a open connection. Similarly for here, primary star with grounded, so this S1 will be closed and P2 is secondary side delta, so P2 will be closed. So S1 and P1 will be open. So we are getting this one. So then after that you can obtain the Z bus. So Z bus here for the positive sequence, Z bus you have to calculate for this network. This is the positive sequence. So here total 2 buses, so you are getting the 2 by 2 matrix. If you are considering this is bus 1 and bus 2. And similarly for the Z bus negative sequence you have to calculate. How we are going to build this Z bus? Already covered in the previous lectures. So we have to just same 4 steps we have to apply here and draw the for the positive and negative sequence, and similarly for the zero sequence. So here the 3 sequence impedances we have to calculate to analyze the fault. So in this way we have to first draw the sequences impedances, then we have to find out the its positive, negative and zero. So here we are going to start the classification of the fault. So basically fault are classified into 2 category, that is called suppose this is the fault. So fault this classified into 2 category. One is called shunt, second is called series. So this is the shunt fault and then called a series fault. Series fault. This is also called a open and this is called a short. This one is also called a short and this one is called a open fault. And this further we can classify into terms of the balance and balance. So fault also classified based on the balance and balance. So one is called a balance case. So balance case, and second is called unbalanced case. So in this way we can also. So these are the faults. So here short or shunt faults, there are several faults are there. We will discuss. And series faults, open faults, when one conductor is open or 2 conductor or 3 conductors. So these are the series faults or open faults. Short faults means or shunt faults, line to ground fault, double line fault or double line to ground fault, or 3 line to fault or 3 line to ground faults. Based on the balance case means triple line to ground faults are the balance, rest other faults are the unbalanced case. Only two faults are the balance. When three phase are become sorted, or they are sorted and connected to the ground. So these are the balance. So they are a different cause of the fault. So this is the abnormal conditions in any electric power system. So cause of the electric faults in the power system is insulation breakdown or compromise. So generally these breakdowns can be occur due to some environmental conditions, due to the human-made conditions, like that environmental conditions are listed here. So lightning ionization, air gaps due to the lightning phenomena, due to the wind, due to the thunderstorms or something. So there are animals or plants coming in contact with the wires, and there is due to the some pollutions. So these are the based on the environmental conditions. There are some insulation breaks. This is also a decay base, decaying the dielectric crystal with the time. So it requires the maintenance. Due to the less maintenance, there is also cause of the faults. So these are the different types of the faults. So this fault is also classified in terms of the symmetrical and unsymmetrical, which is already discussed. Symmetrical balance means system remains balanced. So very common, and we can see that the very rare case we are seeing that the three-phase faults means the triple lines becomes a sorted. So it is easiest to analyze and consider them first for the analysis because it is a balance. So here there is no use of the positive and negative sequence. System is still in balance, but they are supplying the power at a reduced capacity. Unbalanced case means this system is completely unbalanced. So it is a very common, and but for the analysis purpose we are getting a difficulty to analyze this unbalance. So we can use the symmetrical component to convert into the balance systems. So this is the way a symmetrical unbalanced system. So you know that basically the single line to ground fault, that is called LG fault, and double line to ground means line to line fault, and double line to ground faults. These are comes under the unsymmetrical or unbalanced conditions. And symmetrical faults are basically three phase faults. So triple line or triple line to ground faults. Unsymmetrical faults, line to ground LG fault, double line to ground faults, or open faults or short circuit fault. These are the unsymmetrical faults. So here we are just going to start the symmetrical faults. So faults in the power system are divided into three: balanced faults and unbalanced faults, which is already covered. So why we are going to analyze the faults? So here we information from the fault studies are used for the properly relay settings and coordination. So we have to test, or we have to find out the relay settings value as well as their coordination between primary protection as well as secondary protections. There are protection schemes so in the power system network. So we can consider that there is a coordination between these protections or is there or not. We can find out, and how we can set the threshold value of any protection scheme. So that's why we are analyze the fault analysis. So three-phase balanced faults, the information used to select and set the phase relays. So here three-phase balanced faults we can performs, and we can get the information, and we can set the phase relay settings. And also fault analysis used to determine the rating of the protective switch gears like circuit breakers and other devices, measuring devices. We can set their ratings. So magnitude of the fault current depends on the internal impedance of the networks as well as generators. So it depends on the internal networks. So how much? Because so fault voltage divided by the impedances. So impedances is basically related to the generator and networks. So before proceeding to the symmetrical faults, there are certain assumptions. So here the load currents we are considering as negligible. There is no load conditions. So during the faults, we are not going to consider any load conditions. All pre-faults buses voltage are assumed to the equal to 1 per unit. Means T equal to 0, there is a fault occurs. So we have to consider t is equal to 0 minus just before the fault. So we are assuming there is a proper balance conditions and each bus's voltage equal to 1 per unit. Shunt capacitance we are generally neglected. Only the resistance also neglected for the simple analysis purpose, and all generators are running their rated voltage and frequency represented in their rated efficiency and their reactances. These are the certain assumptions. Now we are going to analyze the three-phase faults, that is the balance faults. So in three-phase faults, you need these are the three reactants acting on the generator. These three-phase faults are, we are assuming that this will occur at the terminal of the generators. So these three reactants are there. One is the subtransient reactance, that is represented by XT double dash, transient reactance, this is the XD dash, and synchronous reactance XD. So you know that these three reactants are connected in parallel form when any fault occurs at the terminal of the generator. So this is the XD, this one XD, this is the XD dash transient, and this is the XD double dash. When fault occurs, so all these means at t is equal to 0, there is a fault occurs. So t is equal to 0 plus all these three reactants are acting simultaneously. So overall impedances of the generator will be reduced. So there is a, we are getting very large current. So generally subtransient reactance is used to determine the interrupting capacity of the circuit breakers. So how we are going to calculate the interrupt capacity of a circuit breaker is determined using the subtransient reactance or subtransient currents. While transient reactance is used to set the relay setting and coordination of any protection schemes. So using the transient reactance, we can set the relay settings, either over current relay or voltage or distance protections. We can set the voltage and current rating and also analyze the coordination. If fault impedance is 0, so means there is a solid faults or voltage faults, means Zn will be 0. So when we can say that it is the voltage fault or solid fault. Since impedance of a new path is usually low, so we can excessive current will flow. So this current we can write here IAC in terms of a direct formula we can using. So IAC is equal to root 2 times of IA dash. This is the 1 by XD. XD is the synchronous reactance. XD dash is the transient. XD double dash is the subtransient reactance. So this is the sequential parts into sine omega t plus 5. Here I am not going to derive. So here this is the nature of the fault currents. So when we can see that in the form of the curve, so here you can see the XD double dash and XD dash are the direct axis subtransient and transient reactance. Their range is the subtransient range is the 0.03 seconds, while the transient is the 1 seconds. When we are calculating the maximum AC phase current, we have to take the RMS value divided by root 2, we are getting this form. So this is the nature. So you can say at this point there is a fault occurs. So you are getting that this is the maximum value occurring. So this is the exponentially decay. So in both side. So this is the proper way. And if there is some faults occur in this way, so you are also getting the same nature in decaying. And this is also there is a possible case. So here the maximum DC offset current, that is the steady state current, we can say this is the root 2 IA dash by XT double dash e to power minus t by TA. TA is the armature time constant, generally is the range is given 0.2 second. So now come to the different classification. So there is suppose a three-phase fault occurs at the terminal of the generator. So this condition, so here we are getting this form of the current. So this is the current nature. So there are three segments are there. So here we are getting this form. So we are dividing. So here this period is called as subtransient period, and offered by the reactance offered by the generator is called as subtransient reactance. And after that, this period is called a transient reactance period, and reactance or impedance offered by the generator is called a transient impedance. And current flowing during this condition, this is called a transient current, and there are after that this is the current. So there is this parallel dotted line, this is called a DC offset, or it is called as offset, and this is called a transient current, and this is called a subtransient current. So how we are going to these values we can calculate. So here you can say this value we have to calculate root 2 times the magnitude of IA 0 divided by XD double dash. This is called a subtransient current, maximum peak value. And here we have to consider the same voltage we are considering, only the here the reactance we have to consider the transient reactance. And this is the asynchronous, that is also called the DC offset voltage root 2 EA by XD. So transient generally occurs in first cycle. So they are just considered only 1 or 2 cycles. That is the transient, and a very large AC current is flowing and falls very high rapidly. Decay rate is very high. And transient, decay rate is small, but it occurs if slower rate they are going, so it occurs several 4 to 5 cycles. And steady state it get back to normal conditions. So this is the examples. Here also we consider the 4 bus systems. So bus A, 2, 3, 4. So at bus 2 there is a fault occurs. This is the before fault, there is a network. If there is a fault occurs at bus number 2, then what will happen? So here this is the fault occurs, means there becomes a short circuit. So the neutral point. Then we have to calculate the Z bus for this network. So this is the Z bus. So here 4 bus system, so order of Z bus is equal to 4 by 4. So this is the 3-phase fault occurs. In 3-phase fault, you know that only the positive sequence there. There is no negative sequence, 0 sequence will be there. So here we have to calculate positive sequence Z bus. So we are getting in this form. So you know that the change in voltage VA1, VA2, VA3, VA4. This is the change in voltage at bus 1, 2, 3, 4. We can write in this form, but the fault occurs at bus 2, so it becomes minus VF. And current is flowing, this is minus IF. So current is flowing means coming from the bus, so that's why we are considering the negative, and we have applied the KVL, so you can see this is the negative voltage and this is the Z bus. So we can easily solve these equations in this form. So here the fault occurs at bus 2. When we are multiplying, so we are getting the second columns is the same multiplied by fault current. So all the change in voltage at all the buses, we can see this is the form of the current. So this is the in this way we have to calculate this fault current. So you know that the VF just before the fault, what is the voltage? We know that we can calculate the fault current using this one. So this VF is the nothing but is the Thevenin's open voltage, and this is the Z22 is the Thevenin's impedances. So using Z bus, we can very easy way we can obtain the fault current. And change in voltages, we can calculate del V1, del V2, del V3. After the calculation of this fault current, we can put here, we can get all the buses change in voltage. And its final value we can calculate before the fault voltages plus change in voltages after the fault. We are putting, so we are getting in this form. So we can calculate all the buses final voltage before the fault as well as after the fault in easy way using the Z-bus building algorithm approach. So this is all about the asymmetrical fault analysis. So here one examples I have taken from the reference bus. This is the solve example. So here 4 bus systems which is already considered in the previous example. So at bus number 2, so there is a fault occurs. So this is the 3-phase fault occurs. So we have to calculate the fault currents and voltages as bus 1, 3 and 4, and what is the current flow in the line from bus 3 to bus 1 and current contribution to the fault from the bus 3 to 2, 1 to 2 and 4 to 2. And you have to consider the pre-fault voltages as each buses is the 1 per unit. First, before proceeding, you have to obtain the Z bus of the networks. So this is the Z bus. Here 4 bus system is there. So we are getting the 4 by 4. So then you know that VTH is equal to 1 per unit. And Z bus is equal nothing but equal to Z22. So because the fault occurs at bus 2, so you have to consider this diagonal element. So fault current V Thevenin's voltage divided by Z Thevenin's. So we are getting 1 divided by Z22. So we are getting this is the fault current. And each bus voltages V1, V2, V3 we can use directly formula from this one. So which is already discussed in the previous slide. So we can get that this is the voltage. You know that the bus 2 there is a fault occurs, so we are getting the 0 voltage. And similarly the line current between 3 and 2 1 V3 minus V1 by ZB. ZB is nothing but is the impedance offered by the between the transmission lines. So connected between the bus 3 and 1. So this is the 3 and 1. So we are getting that this is the ZB. So this one is ZB. So ZB is given the A line. This is the transmission line impedance. ZB. So voltage we already know and we can see and we have to divide the ZB. So we are getting this is the current. Same we can calculate for the other. So what are the current contributions? V1 by ZB1. So for the we can get V3 by ZB. So with the bus 2. So bus 2 voltage is 0. So here V1 minus V2. So we are getting the 0. So V1 by ZB1. This is the V1 by V2, V3 and V4 by minus V1. So we are getting their contribution. So in this way we can calculate all the required. So you can see the using Z bus algorithms we can obtain the or we can analyze the symmetrical faults in each way. So overall, the summarize these lectures, we already discussed the construction of the sequence network in positive, negative and zero sequence based on the faults and fault classification, and also discussed the symmetrical fault analysis. Thank you.